In the fast-paced world of technology, 1974 feels like ancient history. That was the year Vint Cerf and Bob Kahn first described the Transmission Control Protocol, or TCP. Fast forward to 2025, and while our devices are billions of times faster, the backbone of our digital lives remains remarkably similar. You might wonder why we haven't replaced it with something modern. After all, we've moved from dial-up to fiber optics, yet TCP still handles the vast majority of our web traffic, emails, and file transfers. It's not just about legacy, it's about a design so robust it has adopted to every generation of the internet. Today, we're diving deep into the mechanics of TCP to understand why this old protocol is still the undisputed king of reliability in a world obsessed with speed.
The primary reason TCP survives is its obsession with reliability. In an IP network, packets are like postcards sent through a chaotic postal system. They can get lost, arrive out of order, or be duplicated. TCP introduces the three-way handshake. First, the client sends a SYN packet, basically saying, "I want to talk." The server responds with a SYN ACK, saying, "I hear you, let's talk." Finally, the client sends an ACK back, confirming, "Great, let's go." This creates a stateful connection. Unlike its faster sibling UDP, which just throws data at the receiver and hopes for the best, TCP ensures that every single byte is accounted for. If a packet goes missing, TCP notices and asks for a retransmission. This guaranteed delivery is non-negotiable for things like loading a web page or downloading software, where a single missing bit could break everything.
But TCP isn't just a delivery man, it's a traffic cop. One of its most brilliant features is congestion control. Imagine if everyone on the internet tried to send data at max speed simultaneously. The routers in the middle would be overwhelmed, packets would drop, and the whole network would collapse in a congestion collapse. TCP prevents this by using an algorithm called slow start. It begins by sending a small amount of data. If it gets an acknowledgement, it doubles the amount and keeps increasing until it senses packet loss. When loss occurs, TCP immediately slows down, giving the network room to breathe. This social responsibility of TCP is what keeps the global internet stable. It's a self-regulating system where millions of independent connections cooperate to find the optimal speed without crushing the infrastructure. Another superpower is ordered delivery. Because the internet is a mesh of different paths, packet number 5 might arrive before packet number 2. If you're streaming a video or reading a document, this would be a disaster. TCP solves this by assigning a sequence number to every packet. The receiving end acts like a librarian, putting the packets back into the correct order before handing them to the application. If a gap is detected, TCP holds the subsequent packets in a buffer until the missing piece arrives. This abstraction is incredibly powerful for developers. When you write code for a website, you don't have to worry about the chaos of the network. You just open a TCP socket and it looks like a continuous, perfectly ordered stream of data. This simplicity for the programmer is why TCP remains the default choice for almost every application.
So if TCP is so great, why did Google create QUIC, and why is HTTP3 moving away from it? The answer lies in TCP's age. TCP was designed when networks were slow and head-of-line blocking wasn't a huge issue. Because TCP insists on order, if packet number 1 is lost, packets 2 through 10 have to wait, even if they arrived perfectly. This creates latency spikes. Modern protocols like QUIC, which runs on top of UDP, solve this by allowing multiple streams of data to move independently. If one stream loses a packet, the others keep going. However, TCP hasn't stood still. New versions of TCP using algorithms like BBR, bottleneck bandwidth and round-trip propagation time, have drastically improved performance on modern high-speed links. We are essentially teaching an old dog new, very sophisticated tricks to keep it competitive.
The biggest reason we still use TCP is the middle box problem. The internet isn't just a wire between you and a server. It's filled with firewalls, load balancers, and NOT routers. Many of these devices were built 20 years ago, and they only speak TCP and UDP. If you try to invent a brand new protocol, these middle boxes will often see it as suspicious traffic and drop it. This is why QUIC had to be built on top of UDP, to trick the existing infrastructure into letting it through.
TCP, on the other hand, is the universal language. Every router on the planet knows how to handle it. Replacing TCP entirely would require upgrading billions of dollars of hardware across every ISP in the world. It's the ultimate example of if it ain't broke, don't fix it, combined with the sheer inertia of global infrastructure.
In 2025, TCP has also evolved to handle the mobile problem. Back in the 70s, computers didn't move. Today, your phone switches from Wi-Fi to 5G constantly. Standard TCP hated this. A change in IP address meant the connection was dead. But multipath TCP, or MPTCP, allows a single connection to use multiple interfaces simultaneously. If you're walking out of your house, MPTCP can start a download on Wi-Fi and seamlessly transition to cellular without the app even noticing. This evolution is why TCP stays relevant. It's not a static document, it's a living standard. From window scaling for high-speed fiber to selective acknowledgements for lossy satellite links, TCP has been patched and upgraded to meet every modern challenge we've thrown at it, often outperforming newer experimental protocols in real-world messy conditions.
Finally, let's look at the ecosystem. Almost every database, PostgreSQL, MySQL, Redis, relies on TCP. Every SSH session, every FTP transfer, and the majority of the web still runs on TCP-based HTTP 1.1 and HTTP 2. While Quick and HTTP 3 are growing, they are primarily used by giant tech companies like Google, Meta, and Cloudflare. For the average developer or small business, TCP is the safe choice. It has 50 years of debugging, documentation, and tooling. When something goes wrong with a TCP connection, there are thousands of experts in tools like Wireshark that can tell you exactly why. In 2025, the value of TCP isn't just in its code, but in the collective knowledge of the global engineering community. It's the most understood protocol in history.
Will we ever stop using TCP? Likely not in our lifetimes. While Quick will continue to dominate the high-performance last mile of the web, TCP will remain the workhorse of the inner internet. The data centers, the internal microservices, and the legacy systems that keep the world turning. It's a testament to good engineering. A protocol designed for a few dozen research computers in the 70s has scaled to billions of users. It proves that a solid foundation, built with reliability and cooperation at its heart, can outlast any trend. So the next time you watch a 4K video or send a text, remember that a 50-year-old handshake is making it all possible. TCP isn't just a protocol, it's the digital glue of the modern world.